Welcome to another new video on strength of materials, that is about thick shells. Here in this video we will be seeing introduction, applications, derivation of Lame's equations, numerical problems. Here I have shown you some images, so let us discuss in detail about them in applications. Let us get into that. Here any cylinder may be referred to as thick if the thickness of the cylinder is greater than d by 20. So if it is less than d by 20, we have to say that as thin shell. That already we have seen in the previous videos. The hoop stress in case of thick cylinders will not be uniform across the thickness. Here I have already told you radial stress is also existing here. Let me draw it here. For example, this is the thick cylinder. So the internal pressure is existing over here. The internal pressure will be maximum at this inner radius, and that inner pressure, if you take at the outer surface, that will be 0. The pressure will be maximum at the inner radius and it will be equal to atmospheric, or it will be 0 at the outer surface. Because as we are saying is 0 because we consider it as gauge pressure, so I am calling it as 0, right? That means the entire this pressure will be consumed by the thickness. To say in formal way, the entire pressure will be eaten by this thickness and it will be 0 at this point. Actually, hoop stress will vary from maximum value at the inner circumference to the minimum value at the outer circumference. That is what I said. As the pressure is maximum at the inner radius, the stress will also be maximum. The pressure will be very less or minimum at the outer circumference. Then subsequently, the stress will also decrease. The pressure is directly proportional to stress. The stress is directly proportional to pressure. The thick shells may be having the internal pressure 0 or external pressure may be 0. So we can see, and that will change according to its function. So let us see applications. Hydraulic cylinders. Actually these things are used to lift or pull or push the machines or heavy objects. These are vacuum chambers and these are gun barrels. These are underground pipes. There is no here you can see vacuum chambers and gun barrel. There is no external pressure. And here for underground pipes there may be internal fluid pressure, also they are having pressure from outside due to this soil. Thick shells will also be used in nuclear reactors and in submarines. You can also collect a lot more applications related to thick shells. Let us get into actual mathematical part. Stresses in thick cylindrical shell. Lame's equations. Lame's has derived a good theory, good equations, and those will be very helpful in finding out the variation of stress across the thickness. I said the stress will not be uniform across the thickness. We shall see how it will be varied, and that can be easily found by Lame's equations. Let us derive them. Assumptions. For every theory there are some assumptions. Material of the cylinder is homogeneous and isotropic. That means all the properties, that means elastic properties, plastic properties, material properties, all these are same or uniform across in all directions. So then we can say that is homogeneous and isotropic. Plane section of the cylindrical cylinder perpendicular to the longitudinal axis remain plane under pressure. So for example, this is a thick cylinder. If you take any section and it is having pressure like this, if you take any section, if you take the cross section of the section, that will be plane. That means that will be flat. There is no bulge. That means all the layers are straining equally. That in technical way, that says that second assumption implies that longitudinal strain is same at all points and the strain is independent of radius. Whatever may be the radius, the strain will be constant. The thick cylinder is subjected to 3 stresses. One is circumferential stress, longitudinal stress, and radial stress. Radial stress I have told you in the previous slide. Let us get into next slide. These are the stresses in thick cylindrical shell. That is the image view. There's a longitudinal section, there is a cross section. In the cross section, the thickness is T and the internal radius I have given to you as R1 and external radius is R2. And here one ring is taken, small ring. That ring, let us draw it separately and let us consider let us analyze the stresses at that point, at that ring. By integrating we will get it, or by applying boundary conditions we can get at inner and outer radius. So let us see the ring here first. So Px is the radial pressure at section x or at the radius x. dpx is the counter pressure acting in the opposite direction of px, and the thickness of the ring is dx. Let us take the section. Here you can see the axis here, x-axis. If you cut along the axis, the view will be like this, 3D view. Here if you take, we have seen the similar image in thin shells also, right? Let us see the same concept will be useful here. Bursting force is equal to resisting force. So what is bursting force here? The force which is trying to split up the shell multiplied by area on which it acts. So where px is acting, so px multiplied by the area on which it acts. So this is the area on which p is acting, internal diameter. So that means px multiplied by 2x is the diameter, because I said radius is small x and this diameter is 2 times the x, multiplied by length. That is not over. That is being reduced by the counter pressure p plus dx. So px plus dpx multiplied by area on which it acts. It is acting at the outer surface of the ring, outer circumference. So I can say that is area is 2x plus dx plus dx, 2x plus dx plus dx into L. So outer portion. So that means that is equal to px into 2xl minus, I'll write it as px dpx, sorry, plus px plus dpx multiplied by the 2x plus 2 2d sorry 2x plus 2dx into L. I can take common here 2L. I will write it as px into x minus px plus dpx into x plus dx. Let us multiply these two terms. What will you get? 2L into px into x minus px into x minus px into dx minus x dpx minus dx into dpx. Dx, dpx are the smaller terms, let us neglect them. And here px plus px into x minus px into x, they will also be cancelled. 2L into minus px dx minus x dpx. These two are remaining terms. I will write it as minus 2L into px into dx minus, sorry, plus x into dpx. Minus is taken common. I will take it as equation number 1. There is a bursting force. So bursting force is over. Let us find out resisting force. The material will offer some resistance against the failure, right? So resisting force, let us calculate. What is resisting force here? Sigma x multiplied by area on which it acts. Sigma x is acting at these two portions, these two shaded parts. Sigma x multiplied by 2 times dx into L. So take it as equation number 2. Let us, in the limiting case, bursting force is equal to resisting force for equilibrium condition. So what is the bursting force here? Minus 2L into px into dx plus x dpx is equal to, what is the resisting force? Sigma x into 2 dx into L. So from that I can write sigma x value is equal to minus 2L into px into dx plus x dpx by 2 dx into L. So 2L cancelled. So minus px into dx by dx, I am separating the terms here, minus x dpx by dx. Now I will cancel them. I'll write it as minus px plus x dpx by dx. So that is the value of sigma x. Remember that. Sorry, this is minus. So let us remember that. Take it as equation number 3. And we have seen the second assumption. Longitudinal strain at any point is constant according to the second assumption given by Lame's theory. So that is nothing but longitudinal direction sigma L, I say, that will be constant. That is equal to, already we have seen in the previous like change in dimensions and strains, we have seen, I will write in the same manner. We have the principal stresses here, sigma L by E, that is the main strain, minus lateral mu into sigma X by E, that is the circumferential stress, this is the longitudinal stress, and another radial stress is also there, and the radial strain will be, that is opposite to the circumferential stress, so that will be plus mu into Px by E. So what will you get now? That will be constant, right? So I will write it as, when it is all constants, you can say this is also constant, this is also having a fixed value, this is also having a fixed value, mu is also having a fixed value, sigma X is a variable, Px is a variable along the radius. So I'll take these two terms, remaining all are considerable constants. So I'll write it as sigma X minus sigma X plus Px is a constant. So I'll take it as constant 2a. So 2a, if you take, that will be easy in calculation. You can take a also, that will be complicated if you take. So 2a, where 2a is a constant, some constant. A is a constant, but I am taking 2a here in order to make my derivation easy, right? So now what will you get here? I will write it as sigma X is equal to 2a minus sigma X is equal to 2a minus Px. In other words, I write it as, in other steps, sigma X is equal to 2a, okay, sigma X is equal to, so when minus Px minus sigma X plus Px is constant, and I can also write it as, when it is constant, sigma X minus Px is equal to also constant. I will write in any manner because it is a constant, just constant, some constant, some constant. So I'll write it as this. So sigma X, I'll write it as 2a plus Px. That constant is irrespective of sign. So I have taken in this manner to make it easy. That's it. So what happens now? Later sigma X value is also having this much, minus Px minus x dpx by dx. This is take it as equation number 4. Equation 3 and 4 both are talking about sigma X. Let us equate them both. So equation 3 is equal to equation 4. So what will you get now? So 2a plus Px is equal to minus Px minus x dpx by dx. That is equation number 3. So what will you get now? So I'll write it as x dpx by dx. I'll write all the terms together, minus Px minus 2a minus Px. So that is nothing but x dpx by dx is equal to minus 2a into, sorry, minus 2a minus 2Px. Let us separate the terms, and I will write it as dpx by dx is equal to, x is taken here, is minus 2a by x minus 2Px by x. So in the next step, I'll write it as dpx by dx is equal to minus 2 into px plus a by x, right? So that again, I will take this term here, dpx by px plus a is equal to dx, cross multiplication here, minus 2 into dx by x. So let us integrate above equations. So what will you integrate it? Take as 1 by px plus a multiply dx, 1 by px plus a dx dpx So that will be written as log bx plus a base e is equal to minus 2 log x plus log b base e. Log b base e is constant of integration, right? You might be having in the lower classes. Let us see now. And we'll get it here. Log e px plus a, that means log px plus a base e is equal to, I will write it as log x square base e plus log b base e, that is equal to log, I can write it as again log b by x square base e, right? Log e px plus a, log px plus a base e, and let us remove log here. Px plus a is equal to, px plus a is equal to b by x square, right? In the next step I will write it as px is equal to b by x square minus g. So this a came here and I have written it as minus g, and let us take it as equation number 5, or let us take equation number Roman 1, and this Roman 1 can be substituted in equation number 4. So what is equation number 4? Equation 4 that talks about sigma x, that is equal to 2a plus px. So in the place of px I will substitute this term 2a plus b by x square minus a. So 2a minus a is plus a, b by x square plus a. That is the value of sigma x. These two are nothing but Lame's equations. So equation 1 and equation 2 are Lame's equations. With these, by finding out the values of b and a, we can find out the stress variation and pressure variation if required. And these values can be found by using boundary conditions. If you do a problem, you will understand it better. Let us get into this. Here the question is, determine the maximum and minimum hoop stresses across the section of the pipe of 400 mm internal diameter and 100 mm thick. So let us first write the data given. So internal diameter is given, that is 400 mm, and thickness is 100 mm, T is 100 mm. When the pipe contains a fluid at a pressure of 8 Newton per mm square, also sketch the radial pressure distribution and the hoop stress distribution across the section. So I will draw it here. What was given is internal diameter. So this was given, internal diameter is 400 mm and the thickness is 100 mm. That thickness will be two sides. So external diameter will be how much? 600. 400 plus 100 plus 100. When the internal diameter is 400 and thickness is 200, with these two I can write the internal radius r1. Internal radius r1 is 400 by 2, that is 200 mm, and external radius is r2, that is 600 by 2, that is 300 mm. And what was given more? When the pipe contains a fluid at a pressure of 8 Newton per mm square, the pressure inside the shell is 8 Newton per mm square. Also sketch the radial pressure distribution and hoop stress distribution across the section. So we need to find out them. Let us write the Lame's equations we have. So we have Lame's equation Px is equal to b by x square minus a, sigma x is equal to b by x square plus a, and take it as equation number Roman 1 and here Roman 2. Let us find out everything. The pressure at the boundary conditions let us apply, otherwise boundary conditions at x is equal to, first one is at x is equal to, at inner radius I can say x is equal to r1. What happens to pressure? That pressure is maximum inside. That is what was given is 8 Newton per mm square. P is 8 Newton per mm square. Right? So now we can say that is, let us substitute these two in equation Roman 1. So what will you get? Px is equal to b by x square minus a, that is 8 is equal to b by r1 square minus a. So that will be 8 is equal to b by r1 is 200 square minus a. So I'll write it as 8 is equal to b by 400 square minus a. I'll take it as equation number 1. Equation number 1, and let us apply second boundary condition. One boundary condition is inner radius, another boundary condition is outer radius. So at x is equal to r2. What happens to pressure? That will be 0 because that is atmospheric pressure. So Px is equal to b by x square minus a is our actual formula. I'll write it as Px is 0, b by r2 is inner radius, r2 minus a, r2 square minus a, that is 0 is equal to b by r2 is 300 square minus a, that I'll write it as b0 is equal to b by 300 square is 940 minus a. Take it as equation number 2. So we can solve equation number 1 and 2. After solving, we will get the value of a as, just a minute. After solving, we get the value of a as 6.4. There are no units because this is constant, and b value is 57600. 57600. The detailed simplification and detailed solution is given in notes. Please download that and see that. So these two values we got. So what we get, b is equal to 57640, 576 576 and a value is 6.4. So after getting these two values, we can find out the hoop stress. What is actually formula for hoop stress? Sigma x is equal to b by x square plus a. So let us find out at internal diameter, internal radius, that is at r is small, x is equal to r1, that is how much? It's 200 mm, and let us substitute it here. Sigma x is equal to b value we have 57600 by sigma x is nothing but at 200 mm. I'll write it as directly x to sigma 200. Here also in the place of x I will substitute 200, that is the inner radius, plus a value we have 6.4. So upon solving, we will get the value as 20.8 Newton per mm square. And sigma 300, that is at outer radius. In the second case, hoop stress at outer radius is, again let us substitute 57600 by x place 300 will occupy, because this is outer radius, plus 6.4. That is how much? 12.8 Newton per mm square. Upon calculation you will get it. So one more task is given to us, to draw the stress distribution across the thickness. So thick shell, I have drawn a part of thick shell here, and this is the center having inner radius 300 mm, so inner radius 200 mm and outer radius 300 mm. Let us draw the stress distribution. I will draw a reference line here, AB. AB is the reference line I have drawn. So with that, let me draw it. So let me change the color. Okay. Here at pressure, what is the pressure here? Inside it is, as given in the question, it is 8 Newton per mm square, and outer it is 0. That is pressure. And at inner radius, at sigma 200 is how much? Sigma 200 is 20.8. 20.8. That is sigma 200 inner radius. At sigma 300, what is at outer radius? What is this much? 12.8. Here It's a clear observation that the stress is varying across the thickness. The stress is maximum at the inner radius and minimum at the outer radius. I hope you understood this. If not, please contact me personally. I will give you homework related to that. You can see the notes for detailed explanation over here. The entire thing is very clearly written over there. You can please download the notes and see that. Please listen to the video and download the notes. So this is a homework for you. Find the thickness of the metal necessary for a cylindrical shell. Internal diameter 150 mm to withstand an internal pressure of 50 Newton per mm square. The maximum hoop stress in the section is not exceed 150 Newton per mm square. I have not told you this type of model, but it was given in the notes. You just see the question, that will be very easy to understand. If you get any difficulty, please let me know, and you can do it easily if you see the notes. The similar problem was solved there. Thanks for watching. Please contact me if you have any doubts.